Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the Fermi Paradox, a quiet reflection on why we are still alone. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The Fermi Paradox explores the contradiction between the high probability of extraterrestrial life and the lack of evidence for or contact with such civilizations. Named after the renowned physicist Enrico Fermi, this inquiry traces its roots back to the mid-20th century. The post-World War II era was a time of immense scientific advancement, leading to the development of technologies that enabled humanity to gaze deeper into the cosmos than ever before. Questions arose in the wake of these discoveries. Given the vastness of the universe, with billions of stars and potentially habitable planets, where are the signs of intelligent life? This region of inquiry is characterized by the absence of the anticipated signals, artifacts, or even the faintest whispers of other civilizations engaging in communication or exploration. The historical context of the paradox intertwines with the advancement of radio astronomy during the late 20th century, which allowed for the systematic search for extraterrestrial intelligence. The Drake equation emerged as a foundational tool to estimate the number of active, communicative civilizations in the Milky Way galaxy. Despite these calculations suggesting a multitude of possibilities, the silence that envelops this search remains a profound enigma, prompting scholars, scientists, and philosophers alike to ponder the implications of solitude in an otherwise rich universe. Born in 1901 in Rome, Italy, Enrico Fermi emerged as a pivotal figure in the evolution of modern physics. His early education laid the foundation for a distinguished career, where he demonstrated a remarkable aptitude for both theoretical and experimental approaches. Fermi's groundbreaking work on neutron-induced radioactivity in the late 1920s significantly advanced the field of nuclear physics. In 1938, amid the rise of fascism in Italy, he and his wife sought refuge in the United States. There, his contributions expanded further, leading to the development of the first nuclear reactor, the Chicago Pile 1, in 1942. This monumental achievement not only solidified his reputation, but also played a crucial role in the Manhattan Project, which Fermi's inquisitive nature extended beyond the confines of nuclear physics. He became captivated by questions regarding extraterrestrial life, pondering the implications of the vast cosmos. This curiosity culminated in what is now known as the Fermi Paradox, which questions why, given the potential abundance of habitable planets, there is no evidence of intelligent extraterrestrial life. His legacy continues to influence contemporary discussions in astrophysics as it invites reflection on humanity's place within this expansive universe, leaving an indelible mark on the quest for knowledge. The Los Alamos conversation in 1950 marked a pivotal moment in the discourse surrounding extraterrestrial intelligence. This setting, a hub of scientific inquiry, fostered discussions among brilliant minds who grappled with the implications of their research. It was here that Enrico Fermi posed a seemingly simple yet profound question about the absence of evidence for extraterrestrial civilizations. the juxtaposition of vast cosmic potential against a void of observable life ignited deep contemplation. Conversations spiraled around the implications of countless stars and planets, many of which could potentially host life. The sheer scale of the universe, a filed life, populated by billions of galaxies, each containing billions of stars, rendered the silence all the more perplexing. Speculations about the nature of life and intelligence emerged, leading to hypotheses that extended beyond mere numbers. This inquiry suggested that the conditions for life, though abundant, may not lead to civilizations capable of communication. The implications of this paradox extend beyond mere curiosity. They touch upon fundamental questions of existence and the nature of intelligence itself. The possibility that intelligent life could arise only to extinguish itself or remain undetected casts a shadow over our understanding of the cosmos. This conversation at Los Alamos remains a touchstone, a reminder of the quiet yet profound mystery that pervades the universe. The search for extraterrestrial life has been systematically approached through equations designed to quantify the unknown. One such formulation is the Drake equation, which seeks to estimate the number of civilizations within our galaxy with which communication might be possible. This equation incorporates various factors, including the average rate of star formation, the fraction of those stars that possess planets, and the number of planets that could potentially support life. Each component of the equation invites both hope and skepticism. The vastness of the galaxy suggests an abundance of stars and planetary systems, yet the conditions necessary for life are far more intricate. The emergence of life itself, along with the subsequent evolution of intelligent beings, involves countless variables, many of which remain elusive. The equation's reliance on estimations introduces significant uncertainty, prompting scientists to continually refine their understanding of these factors. Observations from missions like Kepler and TESS provide valuable data on exoplanets, contributing to a more nuanced perspective on habitability. Despite advances in technology and theory, the conclusions drawn from such calculations often lead back to the same haunting question: where is everyone? In this quiet inquiry, the Drake equation serves as both a tool and a reflection of humanity's innate curiosity about its place in the cosmos. The assumptions behind the Drake equation invite a deeper exploration of the factors influencing the search for extraterrestrial intelligence. Each variable, representing aspects such as the rate of star formation, the fraction of stars with planetary systems, and the likelihood of life developing, relies on estimations that may not encompass the vast complexity of the universe. This region of inquiry emphasizes the uncertainty inherent in defining such parameters. Consider the assumption regarding the formation of Earth-like planets. Current models suggest that these conditions may be rare, yet this conclusion is based on a limited sample size. The exploration of exoplanets has only recently gained momentum, revealing diverse planetary systems that challenge previous notions of habitability. The fraction of planets that may develop life remains equally elusive. Life, as known, emerged under specific conditions on Earth, but variations of life could exist beyond these parameters. The diversity of environments across celestial bodies hints at possibilities beyond terrestrial life forms. The equation also factors in the longevity of intelligent civilizations. The probability of survival through technological adolescence raises questions about self-destructive behaviors. This reflection on existence challenges the assumption that intelligent life will inevitably communicate or explore each variable, while grounded in scientific inquiry, remains a hypothesis, awaiting further discovery in the vastness of the cosmos. Understanding stellar evolution is pivotal in assessing habitable zones around various star types. The life cycle of a star significantly influences its luminosity, temperature, and the potential development of planets within their vicinity. Main sequence stars, for instance, spend the majority of their existence fusing hydrogen into helium. During this stable phase, conditions may be conducive for life in surrounding celestial bodies. As these stars evolve, they transition into red giants, drastically altering their output and temperature. This change can expand or shift the habitable zone outward, potentially rendering previously viable planets inhospitable. The timeline of a star's evolution is crucial, as different types of stars have different lifespans. Massive stars burn brightly yet exhaust their nuclear fuel rapidly, leaving little time for complex life to arise. In contrast, smaller stars, such as red dwarfs, can exist for tens of billions of years, providing extended opportunities for life to develop. The gravitational influence of a star also plays a role in shaping planetary atmospheres. Stellar wind and radiation can strip away the atmosphere of a close-in planet, further complicating the delicate balance required for life. These factors intertwine, creating a complex web of considerations regarding the prospects for life beyond Earth, reinforcing the quiet enigma of solitude amidst the vastness of the universe. The emergence of exoplanet discoveries marks a significant milestone in astrobiology, expanding the horizon of potential habitability. Thousands of these distant worlds have been identified, revealing a diverse array of environments. This region of the cosmos, once considered barren and devoid of possibility, now teems with candidates that might host life. Observations suggest that many exoplanets reside within their stars' habitable zones, where conditions could permit liquid water to exist, a crucial ingredient for life as understood by contemporary science. Advanced technologies such as transit photometry and direct imaging have significantly enhanced the ability to detect these planets. The Kepler Space Telescope, for instance, has uncovered thousands of planetary candidates, each providing unique insights into their atmospheric compositions and thermal profiles. These findings invite speculation on the existence of biosignatures, chemical indicators of life that may be detectable from great distances. Simultaneously, this burgeoning catalogue of exoplanets raises questions regarding the unique conditions that foster life. The diversity observed among them challenges the notion of Earth as an exceptional case. Variations in atmospheric pressure, temperature, and chemical makeup prompt scientists to reconsider the parameters that define habitability. As research progresses, the quest to understand the implications of these discoveries continues to shape the future of astrobiological inquiry, offering new pathways to unravel the mystery of existence beyond our planet. This quest often centers around the Goldilocks zone, a region around a star where conditions are neither too hot nor too cold for liquid water to exist. This delicate balance is crucial, as water serves as a fundamental solvent for biochemical processes essential for life. Within this zone, planets orbit at distances that allow for stable thermal environments, fostering the potential for life-sustaining ecosystems. The parameters defining this region vary significantly based on stellar characteristics. For instance, Stars of different sizes and temperatures generate distinct habitable zones. A smaller, cooler star may have its zone closer in, while a larger, hotter star will extend it further out. This variability introduces a range of possibilities when considering other planetary systems. In addition to distance from the host star, atmospheric composition plays a vital role. A planet must possess a sufficient atmosphere to maintain temperature stability and support liquid water. Atmospheric pressure, along with the presence of greenhouse gases, can enhance or inhibit a planet's ability to sustain life. Researchers continually analyze exoplanets within their respective Goldilocks zones, searching for signs of habitability. These investigations provide critical insights, contributing to the broader understanding of life's potential emergence throughout the cosmos. Each discovery deepens the inquiry into whether we are truly alone in the universe. The search for life encompasses a vast spectrum, ranging from simple microbes to complex organisms. Microbial life, resilient and adaptable, thrives in extreme environments on Earth, such as hydrothermal vents and acidic lakes. These organisms, with their remarkable ability to endure harsh conditions, suggest that life could emerge in similarly inhospitable locales across the cosmos. Beyond microbes, the development of multicellular life marks a pivotal moment in the evolutionary timeline. This transition allowed for greater complexity, leading to diverse forms such as plants, fungi, and animals. Each evolutionary leap introduces new methods of adaptation and survival, reflecting the intricate relationships formed within ecosystems. The emergence of intelligence further complicates the narrative, as it raises questions about communication, technology, and the capacity for interstellar exploration. In regions of the universe, where conditions mirror those of early Earth, the potential for discovering life forms increases. The presence of water, essential for biochemical processes, remains a focal point in the search. Planets and moons within habitable zones offer tantalizing possibilities for life, though no definitive evidence has yet been found. This ongoing quest to identify various life forms underscores humanity's place within the cosmos, invoking contemplation of our existence amidst a vast, largely uncharted universe. Extrema fields embody an extraordinary testament to life's resilience, thriving in conditions previously deemed inhospitable. These organisms inhabit environments characterized by extreme temperatures, pressure, acidity, and salinity, providing invaluable insights into the adaptability of life. In the depths of hydrothermal vents, where scorching temperatures combine with relentless pressure, they flourish, utilizing chemosynthesis to derive energy from inorganic compounds. This process reveals the potential for life to exist far beyond the confines of Earth's familiar biosphere. Microorganisms endure sub-zero temperatures, entering a state of suspended animation. They remain dormant until conditions become favorable, showcasing an impressive capacity to survive prolonged periods without water or sunlight. Such adaptability raises questions about the potential for similar forms of life to exist in the harsh environments of other celestial bodies, such as the icy moons of Jupiter and Saturn. Acidophiles present another remarkable case, thriving in the acidic waters of sulfuric lakes, where few organisms can endure. Their presence challenges preconceived notions of life's requirements, extending the boundaries of where life may exist. These organisms serve as a lens through which scientists explore life's fundamental characteristics, contributing to a broader understanding of resilience in the universe. The study of extremophiles reveals the remarkable adaptability of life, yet raises questions about the barriers that might prevent civilizations from flourishing across the cosmos. The Great Filter Hypothesis posits that at some critical stage in the evolution of life, a significant barrier arises, hindering the emergence of advanced civilizations. These obstacles could manifest at various points, from the initial steps of abiogenesis to the development of complex intelligence. This region of thought considers the possibility that life is abundant, yet intelligent life remains exceptionally rare. Various scenarios could serve as filters, including catastrophic events that lead to mass extinction, environments unsuitable for sustaining complex life, or technological self-destruction. Each scenario introduces a layer of complexity that challenges the progression of sentient beings towards a civilization capable of interstellar communication and exploration. The implications of this hypothesis extend beyond mere speculation. The silence of the cosmos may not indicate a lack of interest, but rather an acknowledgement of the hurdles encountered by civilizations. Understanding these barriers requires an interdisciplinary approach, combining insights from biology, sociology, and astrophysics. Efforts to unravel this enigma contribute to our grasp of life's potential pathways and limitations, illuminating the fragile balance between existence and extinction on a cosmic scale. The quest to understand this phenomenon continues to shape our perspective on humanity's place in the universe. The rare Earth hypothesis postulates that the emergence of complex life is an incredibly rare event. This idea hinges on a multitude of factors that must align perfectly for life to flourish. The presence of a stable star, like the Sun, contributes significantly to this delicate balance. Such stars provide consistent energy, fostering the conditions necessary for life over billions of years. This region of the cosmos, home to a diverse array of planetary systems, reveals that many celestial bodies orbit their stars, yet only a select few possess the necessary attributes to support life. The unique position of Earth within the habitable zone, where liquid water can exist, underscores this idea. Water serves as a crucial solvent, facilitating the complex chemistry of life. Beyond just distance from the Sun, Earth benefits from its large moon, which stabilizes its axial tilt, creating a more stable climate over geological timescales. This stability has allowed for the evolution of diverse ecosystems. The presence of plate tectonics also contributes to a dynamic environment, recycling nutrients and regulating the atmosphere. These factors, combined with the sheer improbability of similar conditions arising elsewhere, lead to the contemplation of Earth's uniqueness. The implications of this hypothesis provoke profound questions regarding the existence of extraterrestrial life and the future of humanity in the vast universe. The lifespan of civilizations in the galaxy plays a crucial role in understanding the Fermi Paradox. This region, where stars form and evolve, reveals a timeline marked by cycles of birth, growth, and eventual extinction. Civilizations may emerge alongside these stellar phenomena, their progress dictated by the resources available and the stability of their environments. Many factors contribute to the longevity of a civilization. Technological advancement can lead to increased resilience, enabling societies to adapt to changing conditions. Yet, the potential for self-destruction through conflict, environmental degradation, or technological mishaps looms large. These ruins of past societies serve as stark reminders of the fragility of progress. In the vastness of space, the intervals between the rise and fall of civilizations may span millions of years. The existence of advanced life forms relies not only on the development of intelligence, but also on the ability to sustain it over time. This raises questions about the likelihood of intelligent beings coexisting in the same epochs, their paths intersecting within the expanse of the cosmos. When considering the silence of the universe, it becomes evident that civilizations may exist, but their temporal existence may not align with our own. The vast distances and timeframes create an overarching solitude, leaving humanity to ponder its place in this complex cosmic framework. Rulkan 40 to Bride, to profound challenge, deeply entwined with the laws of physics. Current propulsion systems rely heavily on chemical reactions, which prove inadequate for traversing the immense voids between stars. Even at a fraction of the speed of light, journeys to the nearest stellar neighbors would stretch over decades, if not centuries. These limitations foster a sense of isolation, as the technological advances necessary for practical interstellar voyages remain largely theoretical. Hypothetical concepts like the Alcubierre warp drive offer tantalizing possibilities, proposing a means to bend spacetime itself. Such ideas, while intriguing, are rooted in speculative physics and often require exotic matter that has yet to be discovered. Quantum mechanics introduces other potentials, suggesting forms of communication that could traverse these distances instantaneously. Yet physical travel remains constrained by fundamental barriers. The implications of these constraints extend beyond mere travel. They shape humanity's understanding of its own existence within the cosmos. The inability to explore neighboring systems reinforces the solitude felt in a universe seemingly indifferent to life's quest for connection. In this silence, the potential for discovery lingers, not as a tangible reality, but as an ever-present reminder of both the vastness of space and the limits of current human endeavor. The notion of reaching out to the stars remains a distant dream, waiting for the breakthroughs that may one day make it attainable. Signals from distant civilizations elude detection, prompting a quest for techno-signatures, evidence of advanced technological activity beyond Earth. This region of inquiry encompasses various forms of electromagnetic radiation, including radio waves and laser emissions, which might betray the presence of intelligent life. The search extends to the infrared spectrum, where thermal emissions could indicate industrial processes or even large-scale engineering projects. Scientists employ sophisticated algorithms to sift through vast amounts of data, analyzing the cosmic background for anomalies. The challenge lies in distinguishing potential signals from the noise of natural phenomena, such as pulsars or cosmic microwave background radiation. A unique pattern, a distinct repetition, or an unusual frequency could signify a message from an alien civilization. This pursuit is not confined to Earth-based observatories. Space-based telescopes, unencumbered by atmospheric interference, enhance the sensitivity and range of detection. These instruments scan the skies, ever vigilant for those fleeting hints of extraterrestrial technology. The strategies evolve, from broad-spectrum searches to focused inquiries targeting specific star systems believed to harbor habitable exoplanets. The quest for techno-signatures represents a convergence of astrophysics and our innate curiosity. Each discovery, or lack thereof, contributes to our understanding of the universe and our place within it, echoing the profound questions of existence that have captivated humanity for generations. The quest for communication extends beyond mere curiosity. It embodies the hope of connecting with potential extraterrestrial intelligence. Various initiatives have emerged, most notably the Search for Extraterrestrial Intelligence, or SETI. This expansive effort employs advanced technology to scan the cosmos for signals that could indicate the presence of intelligent life. By using radio telescopes and other sophisticated instruments, it analyzes vast regions of the electromagnetic spectrum, seeking patterns or anomalies that may suggest artificial origins. The silence experienced during these searches raises further questions. Are other civilizations using different methods of communication, or are they simply not present within our observable universe? This region of inquiry highlights the limitations of current technology, as well as the vast distances that separate celestial bodies. The absence of detected signals may not signify a lack of intelligence elsewhere, but rather the immense challenges of interstellar communication. Current theories propose that civilizations may exist in forms or frequencies beyond our current understanding. It is equally possible that they have self-destructed before achieving interstellar communication, or they might adhere to a principle of non-interference with emerging civilizations. Each of these scenarios deepens the complexity of the Fermi Paradox, inviting researchers to consider the nature of consciousness and the actual parameters of intelligent life. The silence may hold answers yet to be discovered. This vast expanse, the Milky Way, contains an estimated 100 billion star systems. Each star, a potential harbor for planets, suggests a profound scale of possibility. Current research indicates that around 20% of these systems may host planets within their habitable zones, allowing for conditions that could support life. This region, where temperatures permit liquid water to exist, becomes a focal point for astrobiological studies. The search for Earth-like planets intensifies as advancements in detection technology refine our understanding. Instruments such as the Kepler Space Telescope have already identified thousands of exoplanets, many situated in the habitable zones of their respective stars. Yet, the vast distances between these systems create significant challenges for observation and understanding. These discoveries lead to important questions about the nature of life. Even if billions of planets exist within suitable conditions, the factors required for life to arise may be exceedingly rare. The necessary elements, stable environments, and timeframes for evolution must all align perfectly. An estimated 400 billion stars illuminate the galaxy, their light traveling for millions of years to reach us. This cosmic scenery, filled with possibilities, serves as a stark contrast to the absence of signals from potential civilizations. The quietness remains a profound aspect of our existence in this expansive universe. The cosmic timeline offers a framework for understanding life's development, beginning with the Big Bang approximately 13.8 billion years ago. Initially, an incredibly hot and dense state expanded, leading to the formation of fundamental particles. Over time, these particles coalesced into hydrogen and helium, the building blocks of stars. Stars ignited within the swirling clouds of gas, creating the first light in an otherwise dark universe. Stellar nucleosynthesis began, resulting in heavier elements such as carbon, oxygen, and iron. These elements would later prove crucial for the genesis of life. Supernova explosions scattered these materials across the cosmos, seeding new star systems with the essential components for planetary formation. Approximately 4.6 billion years ago, our solar system formed, with Earth emerging as a rocky planet capable of supporting life. Conditions on this young Earth were volatile, but within a few hundred million years, the first simple life forms began to arise in the primordial oceans. Evolutionary processes unfolded over billions of years, leading to an astonishing diversity of life. As complex organisms developed, the planet experienced dramatic shifts in climate and geology, influencing evolutionary trajectories. Each era bore witness to the rise and fall of countless species, shaping the intricate web of life. Today, the silence of the cosmos invites contemplation of what remains undiscovered within this vast timeline. Cosmic catastrophes have shaped the evolution of life and the conditions necessary for its emergence. Asteroids, with their unpredictable trajectories, have the potential to alter planetary environments drastically. When they collide with a celestial body, the resulting impact can cause extinction-level events, reshaping ecosystems and obliterating dominant species. This region of space has witnessed significant impacts throughout history, each one serving as a reminder of the fragility of life. Supernovae, the explosive deaths of massive stars, contribute to the formation of heavy elements essential for life. The shock waves produced by these stellar explosions can trigger the collapse of nearby molecular clouds, leading to the birth of new stars and planetary systems. The remnants of such events enrich the surrounding dust, creating a fertile environment for the next generation of planets. Yet, the radiation emitted during these explosions poses a threat to existing life, potentially sterilizing planets within certain ranges. Extinction events, driven by these cosmic phenomena, force a re-evaluation of the conditions conducive to life. The fossil record reveals patterns of resilience and recovery, indicating that life can adapt and evolve even after significant upheaval. Despite the cyclical nature of destruction and rebirth, the frequency of such events suggests that the universe may be a harsh environment for long-term survival. Contributing to the lingering questions surrounding the Fermi Paradox, the presence of dark matter and dark energy significantly shapes galactic structure and evolution. This unseen mass influences the gravitational forces that bind galaxies together, creating a framework within which visible matter can congregate. Although dark matter remains undetected directly, its gravitational effects manifest across vast cosmic scales, dictating the motions of galaxies and their clusters. Observations reveal that galaxies are not uniformly distributed, but instead exist in intricate patterns influenced by these unseen forces. Large-scale structures known as cosmic filaments emerge, outlining the distribution of dark matter and hosting the majority of the universe's mass. This arrangement affects the formation of new stars and the evolution of existing ones as regions of higher density attract more matter, leading to accelerated star formation. Dark energy also plays a crucial role in the expansion of the universe, counteracting gravitational forces. It accelerates the separation of galaxies, creating a dynamic and evolving cosmic landscape. This expansion raises further questions about the fate of the universe, suggesting that galaxies may eventually drift beyond the observable horizon, isolating them from one another over time. The interplay between dark matter and dark energy creates a complex environment, one that poses challenges for life to establish and thrive. The unresolved nature of these cosmic elements continues to fuel inquiries into the Fermi Paradox. As the silence of the cosmos persists amidst its intricate structure, the Great Silence Dilemma raises profound questions about the fate of civilizations within the vastness of space. This phenomenon suggests that, despite the billions of stars and their accompanying planets, there exists an apparent absence of communication, contact, or evidence of intelligent life beyond Earth. Various hypotheses attempt to elucidate this enigma. One proposes that civilizations inevitably self-destruct before achieving interstellar communication. This theory posits that the technological advancements necessary to reach out into the cosmos may also lead to their own demise. Another explanation considers the possibility of civilizations existing at different stages of development, resulting in a temporal disconnection. It implies that advanced societies may rise and fall within such brief windows of time that they never overlap with others, leaving the universe eerily quiet. Environmental factors play a significant role as well. Some planets may undergo conditions that hinder the survival of intelligent life, rendering them uninhabitable before they can explore the stars. The sociological aspect also cannot be overlooked. Intelligent life may choose to limit their communication or exploration, perhaps due to philosophical beliefs or the desire to avoid disturbing other forms of life. This complex interplay of factors contributes to the ongoing silence, inviting further exploration into the nature of existence within the cosmos. The notion of the zoo hypothesis introduces the idea that advanced extraterrestrial civilizations may be observing humanity, intentionally refraining from contact. This concept suggests that Earth is akin to a wildlife preserve, where humans exist under scrutiny yet remain blissfully unaware of their observers. Such a framework posits that these civilizations choose to observe without interference, allowing natural development and societal evolution to unfold. Evidence supporting this hypothesis can be rooted in the behaviors of various intelligent species. Many animals display heightened awareness of their surroundings, often avoiding human contact. This behavior mimics the potential actions of sophisticated civilizations, remaining detached while gathering data on human behavior and progress. The implications of such an arrangement provoke profound contemplation regarding the parameters of intelligent life and the ethical considerations of intervention. The vastness of the universe, with its countless star systems, amplifies the likelihood of other sentient beings existing in close proximity, contributing to this enigmatic observation. Should these civilizations be monitoring Earth, their intentions remain elusive. The absence of overt communication fosters speculation about their motives and the potential consequences of exposure. This perspective invites a re-examination of humanity's place within the universe, prompting questions about our understanding of intelligence, consciousness, and the intricate web of life that may extend far beyond our known boundaries. The possibility of advanced civilizations self-destructing is a sobering consideration. The trajectory of technological advancement often leads to profound ethical dilemmas and existential threats. It is conceivable that civilizations, in their quest for progress, may inadvertently forge paths toward their own extinction. This region of thought examines the delicate balance between innovation and sustainability. Many factors contribute to this precarious equilibrium. Resource depletion, environmental degradation, and potential nuclear conflicts represent a few of the challenges that may be insurmountable in pursuing ever more sophisticated technologies. Societies might overlook the consequences of their actions. Given that the universe is vast, the likelihood of countless civilizations encountering similar challenges raises further questions. If self-destruction is a common endpoint, the silence of the cosmos becomes more comprehensible. This realization paints a picture of isolation, suggesting that the silence may not stem from the absence of life, but rather from civilizations that have reached a critical juncture and failed to navigate it successfully. Offerfoldathand offertsutathan of deflections of these reflections extend beyond mere speculation, inviting a deeper understanding of the responsibilities inherent in intelligence. It becomes essential to ponder whether humanity will chart a different course or follow the same path as those that came before. The exploration of existence may lead to the simulation hypothesis, which proposes that reality as perceived might be an artificial construct. This concept raises profound questions about the nature of consciousness and the fabric of the universe. If this environment is indeed simulated, the implications stretch far beyond mere curiosity. The idea posits that advanced civilizations, equipped with unparalleled computational power, could create intricate simulations indistinguishable from what is deemed real. Within these simulated realms, conscious entities might experience existence without awareness of their fabricated surroundings. The boundary between reality and illusion blurs, leading to a contemplation of identity and experience. Ambiance. If many intelligent beings exist within these simulations, avas avdorsans affers I semonursus, avasam affersans shrothauj, The absence of contact with humanity could suggest a deliberate choice of isolation or a limitation inherent to the simulation itself. This raises inquiries regarding the motivations behind such creations. Are these simulations mere experiments, or do they serve a greater purpose? In examining this perspective, the vastness of the cosmos appears less daunting. The isolation experienced may not be a reflection of an empty universe, but rather a consequence of the structures governing existence. The investigation into these theories may unfurl layers of understanding that redefine humanity's place within the grand arrangement of reality, leading to an ever-deepening quest for knowledge. The intergalactic perspective reveals an alternate view of existence, avasam urshrizations, avasam urshrizations, one where civilizations, potentially far more advanced, observe the cosmos through their own lenses. These observers, situated in distant systems, might scan the void with technologies far beyond current human capability. They could pass through the radiation and light emitted from celestial bodies, constructing intricate models of planetary systems and environments teeming with potential life. From their vantage points, Earth and its inhabitants may appear as mere blips in a vast ocean of time and space. The blue planet, with its swirling clouds and vibrant landscapes, might pique interest, yet remain enigmatic. The signals escaping its atmosphere, both natural and artificial, could be detected, analyzed, and debated, sparking curiosity about the primitive intelligence inhabiting this region. Potential civilizations might entertain varying hypotheses regarding the apparent solitude. Some may consider factors such as the age of the universe, the distances involved, or the challenges of interstellar communication. Others might explore the possibility of self-destruction, societal collapse, or even deliberate isolation as explanations for the lack of contact. In contemplating the perspectives of these hypothetical observers, it becomes evident that the question of existence and connection transcends individual worlds, inviting reflection on a broader cosmic narrative that remains shrouded in mystery. The search for extraterrestrial intelligence has increasingly integrated artificial intelligence, revolutionizing how data is processed and analyzed. Vast amounts of information collected from deep space observatories and radio telescopes are now scrutinized with unprecedented efficiency. Algorithms are designed to identify patterns and anomalies within this data, searching for signals that could indicate intelligent life beyond Earth. Beyond Earth, these advanced systems analyze the electromagnetic spectrum, filtering through cosmic noise to detect potential communications from distant civilizations. Machine learning algorithms learn from previous data, improving their accuracy in distinguishing between natural phenomena and potential artificial signals. This evolution enhances the ability to sift through billions of signals, narrowing down the focus to those most promising. Collaborative efforts across observatories harness the power of AI, combining resources and expertise in a unified quest. Such initiatives reflect a growing understanding that the universe may harbor myriad forms of life, each with unique characteristics and communication methods. The adaptability of AI allows for innovative approaches to deciphering these potential languages, fostering a deeper comprehension of the cosmos. And this ongoing exploration, artificial intelligence, serves not merely as a tool, but as a vital partner in unraveling the complexities of existence. The pursuit of understanding whether we are alone in the universe continues, driven by human curiosity and advanced technology. Goals for human space exploration are increasingly ambitious, seeking to expand the boundaries of knowledge and experience. Missions to Mars are often highlighted as pivotal steps toward establishing a sustained human presence beyond Earth. This region, characterized by its harsh terrain and thin atmosphere, poses significant challenges for those who aim to colonize it. The logistics of transport, life support, and sustainable habitats require innovative solutions to essential challenges for those who aim to colonize it. The logistics of transport, life support, and sustainable habitats require innovative solutions. Technological advancements are crucial. Robotic systems are being developed to conduct preliminary surveys, gathering data on resources and environmental conditions. These efforts accompany human missions, paving the way for future colonization. The complexities of human psychology in isolation and the effects of low gravity on the human body require careful consideration. Research into these areas continues to deepen understanding and enhance mission design. Challenges also arise from the vast distances involved. Communication delays and the need for autonomous systems become ever more pressing as missions extend beyond lunar orbit. The harsh realities of cosmic radiation further complicate human habitation in space, necessitating robust shielding and protective measures. Efforts to foster international collaboration indicate a recognition of shared goals. This approach may unify diverse capabilities and resources, promoting a collective effort toward exploring the unknown. The future of human space exploration hinges on overcoming these obstacles, with each step taken echoing humanity's enduring quest for connection among the stars. Radio waves serve as a vital link in the quest for communication across vast distances. This electromagnetic spectrum, characterized by its ability to traverse the void of space, has transformed the landscape of interstellar communications. They propagate at the speed of light, enabling signals to journey through the emptiness of bridging the chasms between celestial bodies. The design of radio telescopes allows for the capture of these waves, of entel stas, of these waves, facilitating the collection of faint signals emitted from distant sources. These instruments are often positioned in remote locations to minimize interference from Earth's own emissions. Through meticulous calibration and advanced technology, they can discern meaningful patterns embedded within the cosmic noise. Advances to transmit messages into space have taken various forms, from simple binary codes to complex mathematical constructs, serving as beacons of humanity's existence. The vastness of the universe introduces significant challenges as distances stretch unimaginably, leading to potential delays in any attempted communication. This delay raises questions about the nature of intelligence and the possibility of response. The search for extraterrestrial intelligence relies heavily on these radio frequencies. It is within the range of these signals that the potential for contact exists. The quiet hum of radio waves, emanating from both Earth and distant worlds, of dormant worlds, signifies a continuing hope in the silent expanse of the cosmos. Our current capabilities in detection are constrained by the sophistication of technology and the vastness of space. Instruments designed for astronomical observations often struggle to discern the faintest signals amidst the cosmic noise. Ground-based telescopes, for instance, face limitations from atmospheric interference, while space-based observatories can only monitor specific regions of the electromagnetic spectrum. In the realm of radio astronomy, the search for extraterrestrial intelligence relies heavily on the ability to filter out terrestrial interference. Signals that could indicate intelligent life must be meticulously analyzed, often requiring vast computational resources. The sensitivity of receivers is paramount, yet they can only capture signals within certain frequency ranges. As a result, many potential communications may go unnoticed. Optical surveys, employing advanced imaging techniques, similarly encounter challenges. The sheer distance between stars means that light takes years to traverse the void, limiting real-time observation and response. Spectroscopy, essential for analyzing the composition of distant planets, is hampered by the faintness of reflected light, obscuring potential signs of life. A vast play of technological limitations and our current understanding of the universe creates a stark backdrop. Even as humanity pushes the boundaries of exploration, the search for answers remains an exercise in patience, revealing the profound silence that permeates the cosmos. Each incremental advancement underscores the complexity of this endeavor. The Anthropocene epoch marks a significant chapter in Earth's geological history, characterized by profound human influence on the planet's ecosystems and climate. This period is defined by alterations that extend well beyond local environments, reaching into the very fabric of the atmosphere and hydrosphere. Human activity has introduced unprecedented levels of greenhouse gases, leading to shifts in temperature and weather patterns. These changes manifest as rising sea levels, altered precipitation cycles, and the increasing frequency of extreme weather events. In this context, ecosystems are experiencing rapid transformations. Biodiversity is declining at an alarming rate, with species extinction occurring far faster than natural processes would dictate. Habitats are being disrupted, fractured, and transformed, often resulting in irreversible consequences for countless organisms. The remnants of once thriving biomes serve as stark reminders of the delicate balance that has been lost. Beyond Earth, the impact of human activity extends into space exploration. The introduction of artificial satellites and space debris now occupies the orbits around our planet, creating a new layer of human presence in the cosmos. This accumulation raises questions about sustainability and responsibility as humanity ventures further into the solar system. Reflecting on this epoch invites a contemplation of the future, where the interplay between human endeavor and planetary health becomes ever more critical. The legacy of the Anthropocene will undoubtedly shape both Earth and the broader universe. The Great Filter represents a crucial juncture in the discourse surrounding extraterrestrial life. Speculation arises regarding whether humanity has already surpassed this barrier, or if it lies ahead, shrouded in uncertainty. This concept serves as an explanation for the silence observed within the cosmos, contrasting the apparent abundance of potentially habitable exoplanets. Avise whether balance of potentially habitable exoplanets. In the search for clues, various hypotheses emerge. It is suggested that the emergence of complex life may be exceedingly rare, with countless opportunities for extinction woven into the fabric of existence. This region of thought posits that many civilizations may never reach the technological maturity necessary for long-distance communication or exploration. The fragility of life itself becomes a focal point, where environmental cataclysms or self-inflicted disasters could easily extinguish a burgeoning society. Alternatively, reflections on the nature of technological progress lead to the contemplation of civilizations that advance to a point where they choose silence over communication. The implications of this choice raise questions about the motives behind such decisions, veering into philosophical territories. As humanity continues to evolve, the understanding of our place within the universe shifts. The great filter could serve as a mirror, reflecting the very essence of existence and the choices that shape the trajectory of civilizations. In this quiet contemplation, the future remains uncertain, yet filled with profound possibilities. The implications of contact extend far beyond mere curiosity. It introduces a spectrum of philosophical inquiries and ethical considerations, challenging the essence of what it means to be human. The potential for knowledge exchange could reshape scientific paradigms, igniting advancements in technology, medicine, and our understanding of the cosmos. New frameworks of thought may emerge, urging humanity to reevaluate its place within the vast expanse of the universe. The inherent risks associated with such a monumental event must also be acknowledged. The possibility of misunderstanding or conflict looms large, as two civilizations may not share common values, languages, or intentions. This divergence could lead to unintended consequences, with repercussions spanning generations. The challenge of establishing communication, let alone mutual understanding, poses a formidable barrier. In this hypothetical scenario, the social and cultural ramifications would reverberate through every aspect of life on Earth. Humanity's belief systems, from religion to philosophy, would confront the reality of not being the sole intelligent life form. Global unity may become imperative, as divisions could threaten the fragile peace in the face of an external entity. The quiet contemplation of such a moment invites reflection on the responsibility that comes with knowledge. This consideration urges a re-evaluation of priorities, fostering a sense of stewardship over the planet and its inhabitants in the grander scheme of the universe. The existence of such a paradox invokes profound psychological reflections within humanity. This enigma fosters a sense of solitude, prompting existential inquiries about purpose and significance. The vastness of the cosmos, juxtaposed with the apparent absence of other intelligent life, can lead to feelings of insignificance. Individuals may grapple with the notion that amidst billions of galaxies, the silence is deafening. This psychological landscape invites contemplation on humanity's role in the universe. The absence of extraterrestrial civilizations can reinforce a collective introspection, sparking discussions surrounding ethics, morality, and the responsibilities that accompany intelligence. The awareness of being possibly unique in its sentience encourages a deeper connection to the environment and an ethical consideration of future generations. Conversely, the Fermi Paradox can instill a sense of isolation, resulting in anxiety and uncertainty about the future. The questions it raises may lead to a heightened fascination with exploration and discovery, driving scientific endeavors and technological advancements in search of answers. Such pursuits reflect an innate desire to connect, to reach beyond terrestrial limits. These psychological effects, intertwined with the paradox, reflect humanity's quest for meaning. In the vast silence of the universe, they navigate the terrain of existence, contemplating not only their place, but also the potential of what lies beyond the stars. This quest for understanding deepens their connection to one another and to the cosmos. Imaginations ignite within the realms of science fiction, shaping perceptions of extraterrestrial life. It serves as a mirror, reflecting humanity's hopes, fears, agortrum plides et soc, and aspirations in the face of the vast unknown. These narratives, woven into the fabric of popular culture, provide a platform for speculation about what lies beyond Earth. Characters and worlds, conjured by writers and filmmakers, create a shared vision, influencing societal beliefs about the possibility of intelligent life elsewhere. In this context, they explore themes of communication and conflict, often portraying humanity's place in the universe as both fragile and significant. The portrayal of extraterrestrial beings ranges from benevolent allies to ominous threats, revealing underlying anxieties about the future. These stories foster a sense of wonder, prompting questions that resonate deeply within the collective consciousness. The influence extends beyond entertainment. Scientific inquiry is often emboldened by fictional portrayals. The desire to uncover the secrets of the cosmos is fueled by these imaginative explorations, igniting curiosity and inspiring generations of scientists. As these narratives evolve, they continue to challenge our understanding, inviting reflection on the nature of existence itself. The echoes of these stories linger, shaping expectations and awe. The role of philosophy in addressing the Fermi Paradox invites contemplation of existence itself. Questions arise regarding humanity's place in a vast universe, where the apparent silence suggests a deeper reality. This void provokes inquiry into the nature of life, intelligence, and what it means to be sentient amidst a cosmos teeming with potential. It leads to reflections on why civilizations may emerge yet remain isolated, prompting thoughts on the parameters defining intelligent life and its sustainability. Explorations of technological advancement and its implications on societal trajectories highlight the fragility of civilizations. Each advancement carries the potential for self-destruction or transcendence, creating a paradox within progress itself. In this context, ethical considerations surface, emphasizing responsibility in the pursuit of knowledge. The question of whether humanity is destined to endure or to extinguish becomes ever more pressing. Furthermore, the silence of the universe challenges the assumption of a shared cosmic community. This notion may suggest that intelligent life is an anomaly rather than a common occurrence. Philosophers ponder the implications of solitude in the cosmos, considering whether it enhances or diminishes the significance of existence. In grappling with these existential questions, the Fermi Paradox serves as a mirror, reflecting humanity's aspirations, limitations, and the profound mystery of the universe itself. Exploring the complexities of astrobiology necessitates a multidisciplinary approach, drawing knowledge from diverse fields such as chemistry, biology, geology, and astronomy. Each discipline offers unique insights, contributing to a more comprehensive understanding of life beyond Earth. This region of study investigates not only the conditions that support life, but also the evolutionary pathways that may lead to the emergence of intelligent civilizations. Chemistry provides the foundational building blocks, revealing the intricate processes that forge complex organic molecules under varying conditions. Biological frameworks offer essential principles of life, guiding researchers in examining extremophiles, organisms thriving in harsh environments that mirror potential extraterrestrial habitats. Geology informs the search for environments that may harbor life, analyzing planetary surfaces for evidence of water, minerals, and geological activity. Data acquired from astronomical observations also informs these inquiries, as it highlights the distribution and characteristics of exoplanets within habitable zones. By integrating these disciplines, scientists can formulate hypotheses regarding the potential for life in the cosmos. This synthesis of knowledge enables a holistic perspective, allowing for the consideration of factors such as planetary atmospheres and the stability of environments over geological timescales. New methodologies are emerging within the realm of astrobiology, providing deeper insights into the potential for life beyond Earth. Advances in technology are facilitating the exploration of distant exoplanets, particularly those situated in the habitable zones of their stars. These regions maintain conditions that may support liquid water, a crucial ingredient for life, as understood by current scientific paradigms. Spectroscopic techniques allow for the detailed analysis of planetary atmospheres, revealing the presence of key biomarkers. The detection of gases, such as oxygen or methane, could indicate biological processes at work, sparking further inquiry into the existence of extraterrestrial life. Robotics and artificial intelligence are also revolutionizing the field, enabling autonomous exploration of celestial bodies within our solar system and beyond. These innovations enhance the ability to collect data in environments that would be otherwise inhospitable to human researchers. Theoretical frameworks are evolving alongside these technological advancements. New hypotheses concerning the origins of life, including panspermia and the emergence of life in extreme conditions, challenge traditional views and expand the search parameters. This ongoing dialogue among scientists fosters a dynamic landscape where collaboration across disciplines is increasingly essential. Understanding life's potential diversity enhances humanity's perspective on its place in the cosmos, prompting reflections on existence itself within this vast, enigmatic universe. Wyfontomicthevliaco duisir lorne the peshen bilkendry fleshel, researchers and the public, engaging enthusiasts from diverse backgrounds. Wanding Thiguaith, engaging enthusiasts from diverse backgrounds. It harnesses the collective power of thousands, even millions, of individuals. Volunteers contribute to data collection and analysis, effectively expanding the capabilities of scientific inquiry. This collaborative effort allows for broader surveillance of celestial phenomena, including exoplanet detection and monitoring of atmospheric conditions on other worlds. Enhanced imaging techniques, developed through open-source software, empower citizens to analyze vast amounts of data from telescopes and space missions. The combined observations help refine our understanding of potentially habitable environments beyond Earth. Projects such as SETI at home have transformed personal computers into powerful tools for processing radio signals, capturing faint echoes from distant galaxies. These initiatives not only democratize scientific exploration, but also instill a sense of shared purpose among participants. The contributions of amateur astronomers in identifying transient astronomical events further enrich the scientific landscape, adding depth to the ongoing search. Each observation, no matter how small, enhances the cumulative knowledge base, allowing for a more nuanced comprehension of the universe's potential inhabitants. This collaborative landscape fosters a community united by curiosity, driving forward the quest for answers in the silence of the cosmos. The cosmic perspective offers a profound understanding of humanity's place in the vast expanse of the universe. Vast distances separate celestial bodies, with some stars existing millions of light-years away. This scale underscores the extraordinary isolation experienced by Earth, nestled within a seemingly barren void. The Milky Way galaxy, home to billions of stars, hosts an array of planetary systems. Yet, the silence surrounding potential extraterrestrial civilizations remains a persistent enigma. Galactic exploration reveals an intricate complexity. Each solar system, brimming with potential, harbors an array of conditions, some conducive to life and others inhospitable. The atmosphere of gas giants, the icy surfaces of distant moons, and the parched landscapes of terrestrial planets all stand as testaments to nature's diversity. Among these, Earth remains a singular oasis of life, thriving under a delicate balance of physical and chemical conditions. The search for extraterrestrial intelligence transcends mere curiosity. It embodies a fundamental desire to understand existence. Scientific endeavors, such as the study of exoplanets and the analysis of cosmic radiation, continue to expand the boundaries of knowledge. This exploration serves not only to seek companionship in the silence, but also to reflect on the unique qualities that define humanity. The quiet void of the universe, though echoing with uncertainty, invites contemplation about our origins and future. This contemplation gives rise to several theories, one of which is the dark forest hypothesis. Within this framework, the universe is likened to a dark forest, where every civilization is a silent hunter, aware that revealing its presence could lead to annihilation. This metaphorical forest reveals a stark truth. The vastness of space is not merely empty, but filled with unseen observers. In this cosmic wilderness, civilizations may choose to remain quiet, avoiding communication or signals that could attract unwanted attention. The inherent fear of being discovered leads to a silence that blankets the stars. This self-imposed isolation raises questions about the nature of intelligence and survival. The potential for conflict looms large in the minds of those who contemplate their place in this unforgiving environment. Space, often perceived as a realm of endless possibility, transforms into a perilous expanse, where each civilization operates under the assumption that others may harbor hostile intentions. This cautious approach to existence explains the absence of detectable signals from extraterrestrial life. The vast distances between stars only amplify the silence, creating a profound and eerie stillness. Within this stillness, the implications of the dark forest hypothesis resonate, urging a careful evaluation of humanity's own intentions as it reaches out into the cosmos. The ethical considerations of life beyond Earth introduce complex dilemmas. Encounters with extraterrestrial civilizations may not merely present opportunities for knowledge, but also raise profound moral questions regarding interference and the inherent value of different forms of life. This region of inquiry prompts an examination of how humanity perceives its own supremacy in the biosphere. Acknowledging that intelligence may manifest in diverse ways challenges anthropocentric views, inviting a broader understanding of consciousness and existence. When contemplating the potential presence of advanced civilizations, it becomes essential to weigh the ramifications of contact. The desire for communication must be balanced against the risks of imposing human values onto alien cultures. This possibility evokes the necessity for established protocols that respect the autonomy of those we may encounter. Ethical frameworks must evolve, considering the rights of other sentient beings and the obligations humanity holds toward them. In this context, the preservation of uncontacted civilizations emerges as a critical concern. The decision to intervene or observe has lasting consequences, shaping not only the fate of those civilizations, but also reflecting humanity's moral compass. As exploration continues, the evolution of ethical principles will be crucial, guiding interactions with the unknown and ensuring that the quest for knowledge does not come at the expense of fundamental respect for life. The biochemical foundation of life rests heavily on carbon, a versatile element capable of forming complex molecules essential for biological processes. This unique property enables the creation of proteins, nucleic acids, and carbohydrates, all vital components of cellular structures and functions. In this region of the cosmos, carbon is abundant, allowing various organic compounds to emerge under the right conditions. Water, often regarded as the solvent of life, plays a pivotal role in biochemical reactions. Its polar nature facilitates the formation of hydrogen bonds, leading to the stability of essential macromolecules. The presence of liquid water on a planetary surface significantly increases the potential for life, fostering environments where chemical reactions can occur at a rate conducive to biological activity. Beyond carbon and water, alternative biochemistries are conceivable. Research into silicon-based life forms suggests that, under certain conditions, this element may also support complex structures. While speculative, such theories expand the framework for understanding life's potential diversity across the universe. Astrobiological studies continue to examine extreme environments on Earth where organisms thrive in conditions once thought inhospitable. These findings challenge preconceived notions about habitability, highlighting the resilience of life. With every discovery, understanding deepens, shaping the dialogue surrounding the possibilities of existence beyond our own planet. The prospect of habitable moons presents intriguing possibilities within the vast expanse of our solar system. Europa, a moon of Jupiter, captures attention with its icy crust concealing a subsurface ocean. This hidden body of water, potentially harboring conditions suitable for life, invites scientific inquiry into its chemical makeup and potential biological activity. The surface, marked by ridges and cracks, suggests a dynamic environment, offering clues about the moon's geological processes. Enceladus, another moon, showcases similar characteristics. Geysers erupting from its southern polar region release plumes of water vapor and organic molecules into space, hinting at an active ocean beneath its frozen exterior. These emissions provide direct access to the moon's subsurface, allowing for exploration without the need for extensive drilling. The composition of these plumes remains a focal point of research, potentially revealing the building blocks of life. Other moons, such as Titan, Saturn's largest satellite, present additional avenues for exploration. Its dense atmosphere and liquid hydrocarbon lakes create a unique environment, distinct from the icy realms of Europa and Enceladus. Each moon contributes to the broader understanding of habitability beyond terrestrial confines, expanding the framework of astrobiology. Research missions targeting these celestial bodies promise to deepen knowledge, facilitating the ongoing quest to understand life's potential in the cosmos. The quiet allure of these distant worlds continues to beckon with their secrets yet to be unveiled. Robotic explorers traverse the barren surface of Mars, methodically scanning for signs of life. Despite its desolate appearance, this region harbors a rich geological history, suggesting a once warm environment where water flowed freely. Evidence of ancient riverbeds and mineral deposits indicates that microbial organisms may have existed in the past. Current missions aim to analyze soil samples and the Martian atmosphere, searching for organic compounds or even living microbes hidden beneath the surface. The findings, if any, could reshape our understanding of life's adaptability in the cosmos. Beyond Mars, the icy moons of Jupiter and Saturn present intriguing prospects. Europa, with its subsurface ocean, offers a unique environment where life might thrive in darkness, insulated from the harsh conditions above. Tidal forces exerted by its massive parent planets create heat, maintaining liquid water beneath a thick layer of ice. It is here that astrobiologists focus their efforts, proposing missions to penetrate the icy crust and explore the ocean beneath. Similarly, Enceladus emits plumes of water vapor rich in organic molecules, hinting at the potential for life in its subsurface ocean. These discoveries evoke a sense of anticipation, emphasizing the importance of exploration in understanding life's distribution throughout the solar system. Each mission brings humanity closer to answering the profound questions of existence. The potential for terraforming introduces a concept where inhospitable environments may be transformed into suitable habitats for human life. This process involves modifying the atmosphere, temperature, and surface of a celestial body to create conditions similar to those found on Earth. Mars, often deemed the most viable candidate, presents a landscape of vast plains, towering volcanoes, and deep canyons. The challenges are significant, yet the possibilities are intriguing. Techniques such as releasing greenhouse gases to warm the surface, or introducing genetically engineered organisms to produce oxygen, are deliberated among scientists and visionaries. These organisms could catalyze a transformation, initiating a process that may span centuries. The goal remains to establish a self-sustaining biosphere, one that could support life independently. Venus, with its thick carbon dioxide atmosphere and extreme pressures, poses another challenge. Altering this environment requires innovative approaches to reduce its harsh conditions, potentially enabling human colonization. The implications of successful terraforming extend beyond mere survival. This endeavor raises ethical considerations on the stewardship of other worlds. The question of whether humanity should intervene in these ecosystems emerges, alongside the responsibility to preserve the integrity of existing environments. This exploration into terraforming reflects a broader quest for understanding our place in the cosmos and the capacity for transformation within it. The interstellar medium serves as the vast, invisible canvas between stars, composed of gas and cosmic dust. This region contains the essential elements for life, including hydrogen, helium, and trace amounts of heavier elements. The interplay of these components creates a complex environment where molecular clouds, dense and cold, can form. Within these clouds, the processes of cooling and compression lead to the birth of new stars, illuminating the dark expanse with radiant energy. Cosmic dust plays a vital role in the formation of stars and planets. Tiny grains of silicate and carbon help facilitate the chemical reactions that produce complex organic molecules, the building blocks of life. These grains act as catalysts, fostering the conditions necessary for the emergence of more intricate structures. As stars evolve and eventually explode in supernova events, they enrich the surrounding medium with heavier elements, contributing further to this evolving landscape. In addition to fostering star formation, the interstellar medium also regulates the distribution of energy throughout galaxies. This energy exchange influences the dynamics of star formation and the eventual evolution of planetary systems. Regions of high density become stellar nurseries, where the seeds of future life may take root. The quiet, continuous cycle of birth and death within this cosmic expanse underscores the intricate relationship between matter and the potential for life within the universe. The evolution of intelligence emerges as a complex interplay of environmental pressures and biological adaptation. Through millions of years, certain species have exhibited an increasing capacity for problem-solving, social interaction, and tool use. This trajectory suggests that intelligence is not merely a byproduct of evolution, but a favored trait in environments that demand adaptability. In various ecosystems, the emergence of cognitive abilities often correlates with resource availability and social structures. This region, with its diverse habitats, fosters a myriad of survival strategies. Such adaptability may lead to the development of sophisticated communication methods, enhancing cooperative behaviors that further drive intelligence forward. Highly intelligent species tend to engage in innovative behaviors, utilizing tools that extend their capabilities beyond instinctual actions. The capacity for abstract thinking, planning, and strategizing emerges as advantageous within competitive landscapes. As social groups grow in size and complexity, the need for collaboration and information sharing becomes paramount, reinforcing cognitive development. Evolutionary pressures can favor these traits, leading to a gradual accumulation of intelligence across generations. While the trajectory of intelligence appears to be a natural outcome of survival, the specific conditions that catalyze this development remain enigmatic. The question persists: what unique circumstances are necessary for such evolution to unfold on other worlds, potentially giving rise to life forms capable of profound understanding and exploration? Communication serves as the foundation for the development of civilization. It transcends mere vocalization, embodying the intricate systems of symbols and sounds that allow for the expression of ideas, emotions, and knowledge. In this context, language acts as a vehicle for cultural transmission, enabling societies to share experiences across generations. The emergence of complex language systems marks a critical juncture in the evolution of intelligent species. This development fosters collaboration, as groups can coordinate efforts and share resources more effectively. The nuances in communication also facilitate the establishment of social norms and values, providing a framework within which communities can thrive. Roten language introduces an additional dimension, preserving knowledge beyond the limitations of memory. This permanence allows for the accumulation of wisdom, scientific advancements, and artistic achievements. The ability to record and disseminate information transforms societies, paving the way for technological innovations and philosophical inquiries that expand understanding of the universe. Waroshan will call a bewelty, Thoroshan welti a wifund why stills call universe. In this region of thought, the implications of language extend beyond immediate communication. It shapes identity, influences perception, and cultivates a shared sense of belonging. This intricate web of expression, the timeline of human technological progress, reveals significant milestones, each a silent marker in the larger context of civilization. From the earliest stone tools to the advent of the steam engine, these advancements signify an expanding understanding of the natural world. The discovery of electricity provided a framework for communication, leading to the invention of the telegraph and later, the telephone. Each innovation served as a stepping stone, propelling society forward and altering the landscape of human interaction. As the 20th century unfolded, the development of computers and the internet transformed access to information, enhancing connectivity across vast distances. This interconnectedness has allowed for rapid dissemination of knowledge, yet it simultaneously highlights the stark absence of extraterrestrial communication. Despite the vastness of the cosmos, silence prevails, fostering questions surrounding the existence of intelligent life elsewhere. The implications for the Fermi Paradox become increasingly pronounced. This region of inquiry suggests that, while technological growth may seem linear, the potential for civilizations to achieve interstellar communication could be limited. Factors such as self-destruction, resource depletion, or socio-political instability may play pivotal roles in curbing progress. Each of these elements shapes the narrative of existence, casting a long shadow over the possibilities of companionship among the stars. The quiet contemplation of these questions continues to resonate within the fabric of scientific exploration. The role of international collaboration in space exploration emerges as a vital component in addressing the Fermi Paradox. Shared knowledge and resources provide a collective strength that transcends national boundaries. Partnerships among nations lead to the pooling of expertise, enabling more robust scientific missions. It is through these collaborations that ambitious projects, such as the International Space Station, become possible, fostering an environment of unity in the pursuit of knowledge. Joint ventures allow for the distribution of costs and risks associated with space exploration. By combining efforts, nations can undertake missions that would be unattainable individually. This synergy promotes a diverse array of perspectives and approaches, enhancing problem-solving capabilities in challenging environments. Technological advancements often arise from the cross-pollination of ideas cultivated in these partnerships. Old Waite Enisiprotix. In addressing the mysteries of the cosmos, shared objectives can stimulate a collective curiosity, pushing the boundaries of human understanding. As this region of exploration expands, the collaboration extends beyond governmental agencies to incorporate private enterprises and academic institutions. The interplay of various entities facilitates innovation and accelerates the pace of discovery. Cumulative knowledge garnered from these endeavors contributes to humanity's quest for answers. It is within this cooperative framework that the potential for uncovering extraterrestrial phenomena may be realized, slowly unraveling the enigma of our solitary existence in the universe. Cultural narratives shape the lens through which humanity perceives its place in the cosmos. Throughout history, stories of extraterrestrial beings have captured the imagination, influencing both popular belief and scientific inquiry. These narratives often reflect societal hopes and fears, from utopian visions of advanced civilizations to dystopian warnings of invasion. The recurring motifs within these tales provide a framework that informs expectations surrounding the search for life beyond Earth. The impact of science fiction cannot be overstated. It has inspired generations of scientists and dreamers to explore the unknown. Iconic works have encouraged the pursuit of technological advancements, transforming theoretical ideas into tangible projects. This region of thought fosters a sense of possibility, motivating researchers to seek signals from distant worlds, or to explore the extremes of habitability on barren moons and planets. Conversely, cultural skepticism can inhibit exploration. Narratives filled with disbelief or ridicule can discourage open discourse, creating barriers to collaboration. This duality emphasizes the importance of perspective in the scientific community, where cultural attitudes shape priorities and funding. The quiet hum of curiosity continues to resonate, with collective efforts reflecting a broader human desire to connect with the cosmos, revealing that while we may be alone, our quest for understanding is profoundly intertwined with the stories we tell. The nature of time itself is intricately woven into the fabric of space travel, presenting profound implications for interstellar journeys. Time dilation, a concept rooted in Einstein's theory of relativity, reveals that time is not constant. It can stretch and compress based on speed and gravitational forces. In regions where gravitational pull is strong, time slows relative to areas of weaker gravity. This phenomenon leads to a divergence in experience, especially for travelers moving at significant fractions of the speed of light. As spacecraft venture into the depths of space, the effects of time dilation become increasingly relevant. A journey to a distant star, spanning decades in the frame of reference on Earth, could unfold quite differently for those aboard a fast-moving vessel. While they may perceive only a few years passing, countless years could elapse for observers remaining on their home planet. This disparity raises intriguing questions regarding communication and relationships, as those who travel may return to find a world transformed by the passage of time. Understanding these implications is crucial for future space exploration, presenting both challenges and opportunities. It underscores the need for advanced technologies that can mitigate the effects of time dilation, allowing for meaningful connections between explorers and their origins, despite the vastness of space that separates them. This vastness is shaped by the fundamental force of gravity, which plays a critical role in the processes of star formation and planetary development. Within dense regions of gas and dust, gravitational forces begin to pull matter together. As these particles accumulate, they create clumps that attract even more material, leading to an increase in density and temperature. Eventually, this process ignites nuclear fusion, birthing a new star. Surrounding these nascent stars, remnants of the primordial material continue to coalesce under gravity's influence. This accumulation forms protoplanetary disks, where small bodies collide and merge over time, giving rise to planets, moons, and other celestial bodies. The gravitational interactions within these systems dictate the orbits and eventual stability of the planets, influencing their characteristics and potential for life. While in systems where gravity operates optimally, planets may achieve the right conditions for liquid water to exist, a crucial ingredient for life as we understand it. The delicate balance of gravitational forces can also affect climate stability and geological activity, further shaping the development of these worlds. Understanding gravity's role provides insight into the architectural design of the universe. It reveals the processes that give rise to complexity, serving as a reminder of the intricate connections that bind matter across space and time. The unthd to the delicate balance of Earth's ecosystems, this balance faces unprecedented challenges due to climate change. Rising temperatures impact atmospheric patterns, triggering shifts in weather systems. Glacial retreats expose ancient landscapes, while polar ice caps diminish, contributing to rising sea levels. These alterations not only reshape physical geography, but also disrupt established habitats, creating a ripple effect throughout various life forms. As temperatures rise, many species struggle to adapt, leading to altered migration patterns and, in some cases, extinction. Biodiversity is compromised, which diminishes resilience in ecosystems. This region, once teeming with life, faces increased acidity in oceans, affecting marine organisms and the food chain. The implications of these changes resonate beyond immediate ecological impacts, influencing human existence and potential future developments. The potential for life beyond Earth is intricately tied to these transformations. As conditions fluctuate, the viability of sustaining complex organisms on Earth becomes uncertain. This poses significant questions about the resilience of life, its ability to endure in shifting environments, and the implications for search efforts across the cosmos. The quest for understanding continues, exploring the limits of life in a universe shaped by forces both familiar and alien, driving the inquiry into the nature of existence itself. Astrobiology missions play a pivotal role in this ongoing exploration, providing insights into the potential for life beyond Earth. In the desolate landscapes of Mars, rovers and landers have conducted extensive examinations of the planet's geology and climate. Evidence of ancient riverbeds and mineral deposits hint at a time when liquid water flowed freely, suggesting conditions once favorable for life. These robotic explorers have analyzed soil samples, searching for organic compounds, the building blocks of life. Findings indicate that while microbial life may have existed on Mars, its current status remains elusive. The harsh environment, characterized by radiation and extreme temperatures, poses significant challenges for any surviving organisms. Beyond Mars, missions to the icy moons of Jupiter and Saturn, such as Europa and Enceladus, reveal subsurface oceans beneath thick ice shells. These environments present intriguing possibilities, as hydrothermal vents could support life in isolated ecosystems. The discovery of organic molecules in these regions raises further questions about life's resilience. Each mission contributes to a growing database of knowledge, shedding light on the chemical and physical processes that govern habitability, while definitive evidence of extraterrestrial life remains undiscovered. The data collected fuels theoretical frameworks, prompting scientists to refine their search strategies. Insights gained may eventually illuminate the complexities of life's emergence in the cosmos. The evolution of telescopes has profoundly shaped observational astronomy, contributing to our understanding of the universe. Initially, rudimentary designs offered limited perspectives, constraining the grasp of celestial bodies. Advancements in lens crafting allowed for clearer and more distant views, revealing the vast expanse beyond the Earth's atmosphere. Instruments such as the refracting telescope established foundational methods for observing planetary movements and stellar formations. The introduction of reflecting telescopes marked a significant turning point. Utilizing mirrors instead of lenses, they minimized chromatic aberration, enhancing image clarity. This innovation facilitated deeper explorations into the cosmos, enabling astronomers to catalog previously unseen celestial phenomena. The design continued to evolve, incorporating increasingly sophisticated technology, such as adaptive optics, which compensates for atmospheric distortion, allowing for unprecedented detail. Space-based observatories further transformed observational capabilities, free from atmospheric interference. Instruments like the Hubble Space Telescope have captured breathtaking imagery, revealing galaxies, nebulae, and exoplanets, thereby expanding the known boundaries of the universe. Each enhancement in design and technology has propelled scientific inquiry forward, fostering a deeper understanding of cosmic events. These advancements not only refine our ability to observe, but also provoke deeper questions about existence and the potential for life beyond our planet. The pursuit of knowledge continues, driven by curiosity and the relentless quest for understanding. The search for exoplanets employs various techniques, each revealing distinct aspects of distant worlds. The transiting method, reliant on the observable dimming of a star's light, provides insights into planetary size and orbital period. As a planet passes in front of its host star, even a slight decrease in brightness signals its presence. This approach has led to the discovery of thousands of exoplanets, each contributing to the growing catalogue of celestial bodies. Radial velocity methods, alternatively, detect the gravitational influence of orbiting planets on their stars. By measuring the subtle shifts in a star's spectral lines caused by this gravitational tug, it becomes possible to infer the presence of an unseen companion. This technique offers valuable data concerning a planet's mass and orbit. The results from both methodologies illustrate the diversity of planetary systems and highlight the complexities of stellar environments. These findings suggest a more intricate cosmic landscape than previously understood. Variations in size, composition, and distance from their stars indicate a wide array of potential habitats for life. As researchers refine their tools and techniques, the boundaries of detection expand. Each discovery fosters deeper questions about the nature of these worlds and their capacity to harbor life, perpetuating the cycle of inquiry that defines humankind's exploration of the cosmos. The implications of the multiverse theory introduce a layer of complexity to the Fermi Paradox. Within this vast framework, countless universes coexist, each with its own set of physical laws and conditions. This multitude raises the possibility that life may emerge in forms and environments beyond current human comprehension. The existence of these alternate realities suggests that the factors contributing to the emergence of life are not confined to a single universe, but are instead dispersed across a potentially infinite expanse. This region of thought invites speculation regarding our own universe's unique conditions. In the grand tapestry of the multiverse, the specific combination of elements that allowed life to flourish here may be exceptionally rare. The delicate balance of variables, such as the right distance from a star and the presence of water in liquid form, becomes even more significant when viewed through the lens of countless other realities where conditions differ markedly. The quiet understanding of the multiverse fosters a sense of humility in the face of the unknown. It posits that our search for extraterrestrial intelligence may be limited by the very nature of our existence. As we gaze into the cosmos, pondering our solitude, the multiverse theory serves as a reminder that the answers may lie beyond our current reach, in realms unobservable and untraceable. The potential for space colonization emerges as a beacon of hope in the face of this cosmic solitude. Expanding beyond Earth offers humanity the chance to establish footholds on other celestial bodies, transforming barren landscapes into thriving habitats. Such endeavors could alleviate the pressures of a growing population and dwindling resources, providing a platform for innovation and cooperation. These initiatives are not merely scientific pursuits but also reflections of human resilience and curiosity. Establishing colonies on Mars or the moons of Jupiter and Saturn involves intricate planning and technological advancements. Each mission contributes to a deeper understanding of our place in the universe, creating opportunities for new ecosystems and societies. Unknowns abound in this quest, from the harsh conditions of space to the psychological strains of isolation. Sustainable life support systems will be vital, ensuring that colonies can thrive independently. This region of human endeavor requires not just engineering prowess, but also ethical considerations regarding the exploration and potential alteration of extraterrestrial environments. As humans venture into the cosmos, the possibility of encountering other intelligent life remains uncertain. Colonization may offer answers to the Fermi Paradox, either through the discovery of existing civilizations or by establishing a legacy of life beyond Earth. The universe holds countless secrets, and with each step forward, humanity draws closer to unraveling them. The role of cosmic evolution in the development of intelligent life is intricately linked to the processes that govern the formation of stars and planets over billions of years. Primordial hydrogen and helium coalesce under gravitational forces, leading to the birth of stars. These stellar giants, through nuclear fusion, produce heavier elements, enriching the surrounding regions. The remnants of their explosive deaths scatter these elements across the cosmos, seeding future generations of stars and planetary systems. In this vast expanse, rocky planets orbit within habitable zones, where conditions may foster the emergence of life. The delicate balance between temperature, atmosphere, and liquid water plays a crucial role in determining habitability. Each system evolves uniquely, influenced by its parent star's behavior and the dynamics of neighboring celestial bodies. These processes are not mere coincidences. They reflect the underlying physical laws that govern the universe. As life arises, it traverses a complex evolutionary path, shaped by environmental pressures and cosmic events. The emergence of multicellular organisms marks a significant milestone, paving the way for the development of intelligence. Yet, intelligent life remains a rare phenomenon, often confined to singular instances on planets like Earth. The question arises, is the journey from simple cells to sentient beings an inevitable outcome of cosmic evolution? or an extraordinary exception, ethical considerations emerge as humanity ventures deeper into the quest for extraterrestrial life. The implications of contact with other sentient beings pose profound moral dilemmas. These inquiries extend beyond mere curiosity. They challenge the core of human identity and our place in the universe. The act of searching itself raises questions about the potential consequences of such discoveries. This region of thought encompasses the responsibilities that come with advanced technology. The tools designed to probe the cosmos could inadvertently disrupt fragile ecosystems on distant worlds. They compel a re-evaluation of what it means to respect the autonomy of other civilizations, should they exist. The concept of stewardship becomes essential when contemplating the universe as a shared domain. Each probe, each signal sent into the void, represents a commitment to ensure that exploration does not equate to exploitation. This responsibility extends to safeguarding our planet as well, recognizing that the ethical frameworks employed here might influence how interactions with alien societies unfold. These ruins of our ethical constructs must adapt in light of potential revelations. As humanity contemplates its future in a universe that may harbor life, the search itself becomes a reflection of values. The consequences of this pursuit could reshape not only our understanding of life, but also the moral landscape of existence itself. Funding mechanisms serve as lifelines for astrophysics research, influencing the trajectory of discoveries and the exploration of cosmic phenomena. This region is characterized by a diverse array of financial sources, ranging from governmental agencies to private institutions, each contributing uniquely to the scientific endeavor. Allocated resources dictate the scope and scale of research initiatives, determining which projects advance and which remain dormant. International collaborations often emerge as a response to funding limitations, fostering partnerships that transcend borders and unite institutions. These alliances enable scientists to pool resources, share expertise, and tackle complex questions that no single entity could address alone. The impact of funding is evident in groundbreaking missions, such as space telescopes and interplanetary probes, which rely heavily on sustained financial support to achieve their ambitious goals. Though all are there, the allocation of funds frequently reflects societal values and priorities, steering research toward areas deemed significant or pressing. This dynamic can shape not only the focus of exploration, but also the ethical considerations surrounding scientific inquiry. The pursuit of knowledge is thus intertwined with the realities of financial availability, creating a delicate balance between ambition and feasibility. Each grant awarded has the potential to illuminate new aspects of the universe, yet the limitations imposed by funding remain an ever-present challenge in the quest to understand our place in it. Global politics plays a significant role in shaping space exploration initiatives. National priorities often dictate the allocation of resources, influencing which projects receive support and which remain sidelined. These dynamics can lead to a fragmented approach, where individual nations pursue their objectives, sometimes at the expense of collaborative efforts. In this context, the pursuit of knowledge becomes intertwined with national interests and strategic considerations. International partnerships can foster innovation and shared understanding, yet they are frequently hampered by geopolitical tensions. The complexities of diplomacy manifest in agreements that may stall critical missions or redirect funding towards defense-related technologies instead. Such shifts can hinder progress in understanding celestial phenomena or exploring distant worlds. Competition among nations can drive advancements, pushing boundaries in technology and research. Nevertheless, This competitive atmosphere may also result in a reluctance to share discoveries, creating barriers to collective knowledge. Resources allocated to space exploration can become pawns in broader political games, diverting attention from the fundamental questions of existence and the potential for extraterrestrial life. The consequences of these political influences extend beyond immediate missions, affecting long-term scientific endeavors. This delicate interplay between geopolitics and exploration shapes the narrative of humanity's quest for answers in the vast, uncharted expanses of the universe. This intersection of science and religion reflects a profound inquiry into existence itself. Both realms grapple with the implications of potential extraterrestrial life, each offering distinct perspectives. Science relies on empirical evidence, demanding rigorous scrutiny of the cosmos through telescopes and mathematical equations. In contrast, religious frameworks often embrace faith, positing that humanity's singularity is part of a divine plan. The implications of discovering intelligent life beyond Earth resonate deeply within these contexts. For scientists, it raises questions about the biological and chemical processes that might foster life elsewhere. The quest for answers draws on advancements in astrobiology and planetary science, leading to explorations of celestial bodies within our solar system and beyond. These endeavors seek to identify habitable environments that could support life forms. Religious interpretations, meanwhile, confront the existential weight of such a revelation. The existence of other sentient beings challenges traditional narratives about humanity's unique role within creation. It invites theological reconsiderations, suggesting that divine engagement could transcend human understanding, encompassing a broader cosmic community. This contemplation, at the intersection of faith and reason, fosters dialogue and reflection. The Fermi Paradox, in its quiet complexity, illuminates the deeper questions inherent in both science and spirituality, driving humanity to explore not only the universe, but also the essence of its own existence. Theoretical physics presents intriguing possibilities for interstellar travel, challenging the constraints of our current understanding. Wormholes, as hypothetical passages through space-time, offer a potential shortcut between distant regions of the universe. These structures, if they exist, could serve as portals, enabling movement across vast cosmic distances in mere moments. The mathematics supporting such phenomena arises from the equations of general relativity, suggesting that spacetime can be warped and manipulated under certain conditions. Faster-than-light travel remains a tantalizing prospect, one that eludes practical application. Concepts like the Alcubierre drive propose bending space itself to achieve superluminal speeds, theoretically allowing a spacecraft to traverse distances that would otherwise take millennia at conventional velocities. This notion, while grounded in complex theoretical frameworks, raises profound implications for the nature of causality and the fabric of reality. Research continues to explore these ideas, with physicists contemplating the energy requirements and potential paradoxes associated with such travel. As humanity delves deeper into these theories, the implications extend beyond mere exploration. They invite reflection on humanity's position within this vast cosmos, questioning the limits of technology and the very nature of existence. The quiet pursuit of these answers fuels both scientific inquiry and philosophical contemplation, fostering a deeper understanding of our universe and our place within it. AI-driven research in astrobiology is poised to transform the landscape of our understanding. Advanced algorithms analyze vast datasets, extracting patterns and insights that might elude human researchers. In this realm, the synthesis of astrophysical data with biological principles allows for new models of life beyond Earth. It provides a framework to evaluate potential biosignatures on distant exoplanets, identifying subtle chemical markers that suggest the presence of life. Observations from telescopes, such as the James Webb Space Telescope, yield an abundance of spectral data. AI systems can examine this information at unprecedented speeds, assessing atmospheric compositions that indicate habitability. These capabilities enhance the search for Earth-like planets, guiding the focus to those most promising for further study. The integration of machine learning also fosters collaboration across disciplines. Interactions among astronomers, biologists, and computer scientists cultivate a more holistic approach to understanding life's origins and evolution. Computational models simulate various environmental conditions, predicting how life might adapt or thrive in extraterrestrial settings. As AI continues to evolve, it will refine our hypotheses about the conditions necessary for life. This partnership between artificial intelligence and astrobiology may one day illuminate the question of whether we are truly alone. The future of exploration relies not only on technology, but also on the relentless curiosity that drives humanity to seek answers among the stars. Palm scores. Public engagement serves as a vital connector between scientific inquiry and societal understanding, illuminating the complexities of astrobiology and the Fermi Paradox. Through educational initiatives, informal discussions, and outreach programs, the general populace becomes an integral part of the scientific discourse. This interaction fosters a collective curiosity, encouraging individuals to ponder the implications of life beyond Earth. Vintwy the Anturth interest in astrobiology benefits from diverse perspectives, as questions about extraterrestrial existence and the conditions that may support it resonate within various communities. This collective inquiry inspires novel hypotheses and avenues for research. It is through such public dialogues that the notions of habitability and the potential for intelligent life gain traction beyond the confines of academic circles. Debates surrounding the Fermi Paradox, why, despite the vastness of the universe, no signs of extraterrestrial civilizations have been definitively observed, are enriched by this engagement. They invite philosophical reflections alongside scientific ones, weaving together the hopes, fears, and aspirations of humanity. The unanswered questions fuel public fascination, driving initiatives to search for biosignatures on distant exoplanets. Increased participation in scientific discussions empowers future generations to challenge existing paradigms and seek innovative solutions to enduring mysteries. In this manner, the dialogue surrounding astrobiology transcends the laboratory, becoming a shared human endeavor. The implications of discovering extraterrestrial life extend far beyond the confines of scientific inquiry. This realization would catalyze profound shifts in understanding, reshaping perspectives across multiple disciplines. Fields such as biology and chemistry would experience a renaissance as new life forms challenge established definitions and theories. The examination of their environments may unveil novel biochemical pathways, expanding the horizons of life itself. Philosophically, the existence of other sentient beings raises questions about humanity's place in the cosmos. It invites reflection on consciousness, morality, and the uniqueness of human experiences. Such a revelation could unite diverse cultures, prompting a collective re-evaluation of shared values and beliefs. The dialogue would encompass theological implications, as various faiths grapple with the inclusion of extraterrestrial narratives in their doctrines. Culturally, the discovery would permeate art, literature, and popular media, influencing storytelling and identity formation. The portrayal of alien life in these mediums often reflects societal hopes and fears, serving as a mirror to human aspirations. This dialogue would also manifest in global cooperation as nations unite in the pursuit of knowledge and understanding. Simultaneously, it would invoke a deep sense of responsibility toward preserving both our planet and any newfound ecosystems. The potential need for ethical frameworks would emerge, emphasizing stewardship in the face of newfound interstellar relationships. Patience and perseverance emerge as essential virtues in the realm of scientific discovery. In the quest to unravel the mysteries of existence, researchers often contend with vast stretches of time and uncertainty. The slow accumulation of knowledge through meticulous observation and experimentation allows for the gradual unveiling of the cosmos's secrets. Each hypothesis built upon earlier findings contributes to a broader understanding, fostering an environment where curiosity thrives. This region of inquiry demands resilience in the face of setbacks. Failed experiments and inconclusive data can lead to frustration, yet they serve a vital purpose. Each misstep provides insight, guiding future explorations and refining methodologies. The iterative process of trial and error, while often arduous, the pursuit of understanding the silence of the universe necessitates a long-term commitment. Researchers work tirelessly to enhance instruments and methodologies, striving to detect faint signals from distant civilizations. Each advancement, no matter how incremental, brings humanity closer to a moment of revelation. In this context, the quiet resolve of scientists across generations forms the backbone of exploration. Their collective efforts, driven by an unwavering belief in the importance of inquiry, illuminate pathways through the unknown. The journey itself becomes as significant as the destination sought, fostering a legacy of knowledge that transcends time and space. The search for answers continues, enveloping humanity in a quest marked by curiosity and wonder. In the vastness of space, the absence of detectable intelligent life prompts profound questions about existence and purpose. Each signal received and every distant star observed serves to deepen this exploration, illuminating the contours of solitude that characterize the cosmos. Although efforts to understand this phenomenon extend beyond mere observation, embracing the realms of philosophy and science, research into the conditions necessary for life reveals the delicate balance of factors that may limit the emergence of intelligent civilizations. This scrutiny unfolds in the context of evolving technology, allowing for a more comprehensive examination of the universe's myriad environments. The silence encountered thus far may not solely indicate a lack of life. It could reflect the fleeting nature of civilizations, where technological progress and existential threats coexist in a fragile equilibrium. The questions posed by the Fermi Paradox invite a re-examination of humanity's own trajectory, encouraging introspection on our responsibility as stewards of the planet. In this vast expanse, the uniqueness of Earth becomes paramount. It is within this solitary realm that the quest for understanding continues, fostering a legacy of inquiry that may one day bridge the silence of the universe, revealing the profound connections that lie hidden in the cosmos.